Like, oh, it's a terrible story. They died immediately.
All done?
Doing a nod now?
No, because I might do a nose now if I can get a focus. I might nose now.
And my average cost per round. I put
I kind of like left that at home.
Kevin. It's, well, I don't know. It's not that hard except
I got the multiple choice done.
the multiple choice is fairly easy. It gets really a lot more difficult. Yeah,
I am now the teacher. Obey me. Whoa, what is your... I just noticed your sweater. What? Oh.
They're all stand-ups.
Oh, I see.
I was thinking that maybe I just tape a mirror to a sweater, but I don't know. I feel like
Tape a
that...
mirror?
Yeah. But that might raise questions from teachers.
All right.
It's like, yeah, you're
Make sure you're like always like facing. We're gonna stop it.
If you're sitting near the buzzer, feel free to shut it off.
I think she can.
No, just keep it going. It's not going to be true. Just want to shut that off. Okay, that's super cool.
Think about what things
Me.
just all in different ways. You just tap in different ways and they'll come out.
Alright. So we've got all these graphs up front, and the first question for you on the pear deck is, what patterns do you see when you look at all of these boards here? And by all of them, I mean the purposeful ones. Take that. That's like a topical. So again, first question on the pear deck, what patterns do you see to this? What up? That is not the right one. Sorry. The right one is RQGUK. Okay, so things our friends are noticing here. What happened to that? That I had 3 of these. There we go. So linear change of position along the x-axis, but a parabolic change of position along the y-axis. Velocity on the x-axis looks fairly constant, save for a couple of those. Velocity on the y-axis is never constant. Seems like all the x position and x velocity and y velocity graphs are linear, except for Hufflepuff and Durmstrang. The x velocity graph has a slope close to 0. So in most cases, right, we see, except for these two, x velocity versus time graph that's pretty close to 0. So again, it's important that you pay attention to parameters and not just build a spaghetti tower to build a spaghetti tower, but pay attention to the marshmallows. So when we need to look for something later, we can find it. Okay. Otherwise, you're never going to science. You're going to be really good at being told what to do and then maybe regurgitating it, okay? But I'm just a boy standing in front of a room trying to ask them to think critically, okay? So thanks to most of you for being purposeful about it. We've got constant velocity on the x, and then you don't have that on the y. What do you have going on the y? Let's kind of direct our attention to that, okay? So what do you notice when you take a gander at the y position versus time and the y velocity versus time graphs? Let's make it specific to those. We're just looking at the y graph, so just the boards on the, or just the part of the board on the right side of the board. So I'll do this, maybe. Bollocks. Okay, so things our friends are noticing here, y position is parabola, y velocity always becomes a constant downward sloping graph after some time. That time is after it's been thrown, so we don't need the stuff prior to the throw. And so we kind of ignore that business, yeah, okay. Y position parabolic, y velocity constant slope, that does not equal 0. Sometimes the y velocity starts out with a positive, dang it, and then somebody says negative acceleration, okay. So negative acceleration, let me throw that at you. What do you notice about the accelerations? Is there any kind of rhyme or reason to those? This is why it's helpful when you write large so we can see things from farther away. So, yeah, hit me up.
I have to leave right now. That's why I'm
I hope you have it ready.
Should I just leave this on your desk?
You can put it in the basket.
Yeah. All right. So
Things we're noticing. Let's see here. All right, what are our friends saying here? Accelerations are negative, constant mostly. Mostly. It's the worst when like somebody's replying to your text and then they're just erasing. Around 10-ish meters per second, aka gravity. Insert Owen Wilson.
Wow.
Sound. There we go. Okay. Acceleration is constant and negative. Acceleration of x is 0. Acceleration of y is negative. Okay. Acceleration on the y velocity graph is negative. Seems to be close to negative 12 meters per second squared for most of them. Vertical acceleration seems to vary around negative 11 meters per second squared. What might be a reason for some of the differences that we see in those acceleration values? Let me throw that at you.
Human error.
If you say that in here, you get taken to the guidance office and asked to drop. So, not asked, told. Okay. What might be a reason for some of the numbers? Because I see as little as 8.54. I see as much as 12.4. And then where's my 1? All right, so let's ponder this for a second. So different balls, mass and size, different initial final velocities, different kind of ball, okay? The balls that were involved here were duct tape, bowling, and basket. And this thing up and running. Oh, come on, man. Jessica, could you be a buddy? There's a volleyball up front on the shelf. Yeah, bottom shelf.
I dislike.
Math.
All right.
No, when teachers just straight up give you like.
My basketball got borrowed, so we're gonna have to approximate it as a volleyball.
Yeah, it's not that one.
Sorry.
Yeah, I'm in AB. He just gives us the.
So I've got a volleyball here, and when I put it on the scale, it's about 3 newtons. Okay, the basketball's like 7. Okay, but that's about what that is. So 2 or 3 newtons for the volley. 26-ish for the duct. About 64 for the bowling. Okay, so let me write those numbers down somewhere for us. Projection. There you go. So we've got. Wow, that's a terrible B. That's not how you spell basketball. Basketball. Yeah. Basketball is about 7 newtons. Duct tape is about 20, what was it? 20 something? Say 26 newtons. Bowling is about 64 newtons. Okay? So, yeah, we can order these. Well, we could if people wrote stuff like they were asked to do. What is it?
Duct tape.
Duct tape.
Yeah.
Okay. So we can order these based on the accelerations. I think the biggest one overall is this one. It's 12.4. Has anybody got a number bigger than 12.4 on here? Ooh, it's in the ballpark of. And then we've got low 12s. Let's see, low 12s. Gravity. Persistent. Duct tape balls going over here. My first day. you want to be on that side. Okay. And where do you go? All right, so I've got these ordered from greatest to least in terms of slope. This is negative 12.4, negative 12.4, negative 12.2, negative 11.6, negative 11. Let's call that negative 11.8, negative 11.7, negative 11.2, negative 10.8, okay? So in looking at that, is there a pattern as to the acceleration and the type of ball that's involved? In other words, basketball is the lightest, bowling ball is the heaviest. Is there kind of a pattern to that? Okay. So run that by your neighbor and then run it by the pair deck. Are the differences in acceleration explainable by the different ball that was used? What? 26. Oh, sorry. Back here. As far as I know. Some kid made it my first year because we didn't have Chromebooks, so you couldn't play 2048 on class. So we just played with duct tape. All right. All right, so let's look at some of the responses here then. Acceleration is greater for the lighter balls because it requires less force to change its y velocity. Basketball is the lightest, has the largest acceleration. Maybe there's a difference between the type of ball and their accelerations. They seem to be grouped, but it doesn't really make sense because medium match ball has the smallest acceleration, but the heaviest and lightest are the closest. Lighter balls tend to accelerate slightly faster. Material does matter. Nah, dude. Basketball has the largest acceleration, followed by the bowling ball and then the duct tape. Not sure what the reason is, but it does look like they fall into a pattern. Basketball's biggest, duct tape has the smallest size. Okay? So this is like why my hackles get up when the Eddie Wilsons of the world say things like human error. And this is why I wanted multiple people in your group to do the analysis. Okay? Because if multiple people in your group are doing the analysis, we can make comparisons amongst the values that they get. Now you look at Ravenclaw, clearly one person did it and the rest just copied off of them. But if you look at Dumbledore's army, these appear to be honest folks. Okay, why do I say that? Yeah, how much does it vary? From the high to the low? 1.6, yeah, okay. And then when you look at some of these other boards, if you go with that kind of variation, I mean, these people are looking at the same video, and somebody got negative 11.8 and somebody got negative 10.2, okay? Or if you look at Hufflepuff, these are good, honest people as well. Negative 8.54 to negative 10.85. What's that? That's 2.3. They're looking at the same video. They're getting accelerations that different. What does that tell you about the values of the accelerations up here? Okay, this is the thinking part of things. So when you look at the Dumbledore's Army board, when you look at the Hufflepuff board, okay, they had 3 people in those groups try that thing. What does that say to you to see the values that they're posting up there for the accelerations? Go ahead and be specific about this. You did the lab yesterday. What do you think are some reasons that we might see that in terms of the numbers that are being reported? Try to come up with one or two things. Just don't say that one thing. Unless you want ants, because that's how we get ants. All right, let's see what our friends had to say here then. You have to take the values with a grain of salt. People probably chose different points on the ball, collected different amounts of data points. Okay. Should the point on the ball, if you chose the top or you chose the bottom, would that affect the acceleration that you got?
Yeah.
So the bottom of the ball is accelerating differently than the top part of the ball? Isn't it a solid object? Sir?
Well, if you press like, if you weren't exactly at the same spot, it would be changed. It would be a different type of distance. It would be a different distance traveled on your pixels.
That's it. So that's an excellent example of one of the difficulties of the lab, is because making sure you tag the same point on the ball is pretty important, but pretty tough to do, right? Because what happens to the ball in the video?
It moves.
Well, it moves, and also in the video, is it a ball?
Yeah.
Sometimes it's kind of a, yeah?
It's a little bit blurry.
A little blurry, a little distorted. Okay, so it is tough to consistently tag the same place on the ball. Intervals that people measure could be different, which would affect the slope since there are fewer points at different times. I don't know about that. If you look at your graph, if you remove some points from it in the video analysis, you're still going to have the same general line. I don't know that you're going to get a different slope. You just have fewer points on the line. Okay? Initial final spotting, not completely following trajectory as well as point amounts. Be honest, it's pretty damn hard with that touch screen to consistently put the dot on the same part of the ball. That's not human error, that's measurement uncertainty, okay? And so I want to establish that so that when you look at the values up front, and you see Dumbledore's Army with a range of -10.2 to -11.8 for the same video, and you see Hufflepuff with a range of -8.54 to -10.85 for the same video, should I look at a board for Slytherin where I see 11.6 and see that as different from the slope that I have over here for Ravenclaw, where they're closer to like 12.1? Okay, that's what I'm trying to establish for you right now. Are these slopes different? I mean, they're differing by like 4 or 5 tenths of a meter per second squared. Okay? This is the same video, and it's differing by 1.6 meters per second squared. So when you're looking at these numbers, they're reported in a lot of cases to 4 digits, but what's the issue with that? I mean, I don't think we know it quite that precisely. So I just want you to have that awareness so we can kind of get rid of a lot of these extra digits here. Oops, that's a unit. Quinn, you were going to add something?
I was just gonna say they're like within the realm of like acceptable error. They're essentially the same.
I would sub in the words measurement uncertainty there, but we're on the same page, right? When you look at this, -12 and -10, that's the same graph, okay? Over here, -8, -10, that's the same graph, okay? So your slope value, really it's plus or minus 1 meter per second squared. And when you look at it through that lens, is this basketball graph any different from this bowling ball graph? Any different from this duct tape ball graph? Is there a difference based on the ball used? measurement uncertainty would seem to indicate that they're not significantly different, okay? In other words, if we kind of like mentally average these, where are we going to shake out at? 12 plus 12 plus 12 plus 12 plus 12 plus 10 plus 11 plus 11 plus 11 plus 11 plus 9 plus 10 plus 8. Quinn, what's that average to mentally?
I don't know. I'd say around 10.
Boom. Okay. I need to play ball. There you go, right? Kind of shakes out somewhere in the ballpark of 10. Okay? 10 meters per second squared. In the ballpark of. Okay? And again, I'm establishing that we're in that ballpark based on the variance that we see here. Okay? This range is from -8 to -10. This range is from -10 to -12. Okay? Based on that amount of variation, if you're getting 11 or you're getting 12 for that slope, yeah, it's in the ballpark of 10. And why should that be significant? Well, let's pop back on over to, take that back. Before we go away from this, the last question I want to ask you while we're looking at all of them, do you see evidence of any models that we've studied previously up here? Okay? Do you see evidence of any models that we've studied previously when you look at these graphs? I don't want to do that. I'm on the wrong Pear Deck on this computer. All right, so I need you to be specific, okay? Which graph do you see which model on, okay? So can you go in and edit that real quick? I see evidence of the blah, blah, blah PM on the blah versus time graph. Because the graph is blurred.
Is that a laser, dude?
All right, what are our friends saying here? So, UBFPM and CAPM on the y velocity graph. Explanation is good too, right? So I'm looking for that as well. So, because velocity graph has a constant slope, okay, constant non-zero slope. CVPM for the x graph, because the position versus time graph has constant slope, and in most cases, right, the x graph, the x velocity versus time graph is horizontal, right? So this thing is doing two things at once. It's doing CAPM in the y. It's doing CVPM in the x. It's doing both of the things that we've studied so far, and it's doing them at the same time. So I want to try to get some insight into what's happening there, okay? So, thing. Boop. Hey, there we go. Right? So here's our friend, basketball, duct tape ball, bowling ball. Let me do this. I want to take a look at one of those videos. And let's look at oh gosh, let's look at the Death Eater video here, huh? Okay? So the Death Eater video, what does a free body diagram look like for the basketball at this point in the motion? Okay? So I've got the ball there. Drop it onto here. What do you think? What would a free body diagram look like for the ball at that time? And then let me give you that screen. Where's that at here? Give me a second, sorry. Ooh. I'm going to ask you to draw 2 free body diagrams. Draw one for the ball at this way, let's say on its way to the top. Draw another free body diagram for the ball at the very top of the motion. Okay? So if you can imagine, if its path was something like this, let's say a free body diagram at A and a free body diagram at B.
This is physics. You know air doesn't exist. Doesn't perish.
Poop on you. Stop changing your minds, people. All right. Oh, man. Stop it. All right. So let me see if I can find. There we go. All right. So I need you to consider those 3 situations with your neighbors real quick. What are you liking or not liking about them? Maybe go with this. That didn't work. Here we go. All right. So here's one. There's their A and B. Here's another one. There's their A and B. And there's that one. There's their A and their B. So let's call these. I can't write on this freaking board. Nope, that'd be too convenient. All right, so imagine that I had the capability to write on this board. And I wrote the number 1 here, the number 2 here, and the number 3 here. Ask a question of that person. Okay, let me flick it over to a question asking panel. Oh, Pear deck. Okay, so that's what we're looking at. So person 1, 2, and 3, and then boop. Nope, not draw a graph. Let's go words. There we go. All right, so I'll ask you a new one. All right, so a question for those fine folks. And now I got rid of the thing back there so you can't see what's what. All right, so here's kind of the main questions. 2 and 3 What are your feelers and dealers? What is the force pushing the ball up? Why is there force going up on the ball even after they've left the thrower's hand? What is the smoosh push dealer? What is pushing on the ball? What does the up arrow number 3 indicate? Is there acceleration along the x-axis? What's lifting the ball up in the air? What is the name of the upward force? What are the two forces acting on the ball? Where is my charisma present? What are the upper forces? What is acting on the ball to give it the dihedral vector at point A? What is the horizontal acceleration of the ball at 3? What are the force related from 3? How much wood could a woodchuck chuck? A woodchuck could chuck wood. What year did Bismarck unite the German states? Somebody's got a gum test. Okay? So take those things on board. Go back to the free body diagrams that you have. I'll take you there myself. And okay. Go back to your free body diagrams and consider those questions, okay? And if you were looking like number 2 or like number 3, which there are a few in here, you got some explaining to do. Again, our definition of force is an interaction between two objects. If you're going to draw an arrow, you better be able to state which two objects are interacting.
No, that is not a good one.
Now it's looking like this, okay? Now it's looking like this everywhere, okay? So you're kind of picking up on this. So let's go back over to our dear friend, the OneNote. And if you've got, this is the basketball. So if I'm drawing the diagram at A, it's going to look like this. This force is 7 newtons, okay? At B, the diagram looks like this. This force is 7 newtons, okay? Balanced or unbalanced? Unbalanced. How unbalanced is it? It's unbalanced. 7 newtons in the downward direction in both cases. Okay? So acceleration is Fu over mass. Acceleration, I've got an Fu of 7 newtons. Anybody happen to know the mass of the basketball? 0.7 kilograms. I'm going to get an acceleration of 10 meters per second squared. Okay? If I did this, if I did this for the bowling ball, I would have an FBD that showed a force gravity of 64 newtons. That would leave me with an Fu. An Fu of 64 newtons. Fu over M equals A. Please just work, you sad thing. Okay, 64 newtons. Eddie, are you controlling this with your mind again? Knock it off. What's the mass of a 64 Newton bowling ball? 6.4 kilograms, Mr. Harding. Okay, thanks. So then I shake that out. I'm going to get an acceleration of 10 meters per second squared. Oh, by the way, we should be drawing an acceleration arrow here. What direction is the acceleration arrow pointing? Down, a.k.a. the negative y direction. Okay, it's pointing in the negative y direction. That's why in all these cases, you're seeing a Vx graph with an acceleration of what? 0, because there's no acceleration pointing in that direction. And you're seeing a Vy graph with an acceleration that, when taking measurement uncertainty into account, is certainly well within the ballpark of 10 meters per second squared. Okay? These balls are not traveling fast enough or far enough for air resistance to be significant. Keep in mind, we dropped a 1970s era man in a Speedo off a 50-meter tall tower, and air resistance was not a significant factor on him. So I assure you, at the speeds that Mr. Audie and I play catch, you're not going to have significant effects due to air resistance. Okay? Maybe if we involved, are any of you sports people in baseball or softball? See? Yeah, so you don't have to worry about air resistance in your lives. All right. But yeah, I mean, that's kind of the long story short of this. So because the FU is acting only in the vertical direction, you have in the y-axis CAPM. CAPM because UBFPM. But then if you look at it side to side horizontally, there's no unbalanced force in the left to right direction. So the x-axis is CVPM because BFPM. It's doing everything that we'd studied to this point, but it's doing it all at once. So what's really cool about projectile motion problems is they're not one problem, they're problems. Okay, each projectile motion problem is a CVPM problem for the horizontal axis and a CAPM problem for the vertical axis. So every problem that I assign, you're going to have both a CVPM and a CAPM problem in here. Okay. What more needs to be said on that? Let's see if we can flip over to this thing quick. Oh, I need to find the world's biggest remote control. Anybody see it? Can't Laserdisc without it, Mr. Hart. Sad face. Ooh. Nope, that's a friend. All right. We'll have to pick up with that video in January. What I have for you is a new idea in physics. It's called reading, okay, out of the book. Sections 4.2. We're going to read pages 85 to 88 over winter break. So split it up. Do a page and a half each week, and it won't seem like that much, okay? I'm going to have some videos on Canvas that talk about the problem-solving techniques. Basically, it's just a matter of resolving the problem into the X part of the motion and the Y part of the motion. And then there's a mastering on projectile motion that's going to be due after we get back, because, yeah, you're going to Cabo, you're not going to have time, there's no internet on the cruise ship. But if you got time, because your life is sad because your parents are teachers, then, you know, you can get this done. Mastering estimates that it's 90 minutes. They're mostly tutorials and videos, okay? All right, go ahead and send somebody by to grab your board from the front, clean it up, and have yourself an excellent break.
Yeah,